Good afternoon, statisticians. I messed up towards the end of the last video, so I don't know. I just had a hard time trying to really remember how to get the normal distribution. But guess what? I'm going to show you three ways to do that right now to start this video. I know it's 7.3. Just had a moment. Sometimes you get confused doing so much of this stuff. So here we go. I'm going to show you that first, just three ways to get that z-score. And then I'm going to jump into 7.3, which is like the same thing we did, population means, but now we're just going to figure out population standard deviations. So I'm going to share my screen, and the first thing I'm going to do is show you three ways to get that z-score. All right. So this is just a little recap of what I messed up at the very end of the last video. Z-scores, is they come from the normal distribution. But because we're cutting it in half, this alpha level has to be cut in half. That was the one mistake I kept making. And guess what? We're all human, right? We all make mistakes. So if I'm at 95%, right, this means I have 5% kind of left over on both sides. 95% is here. So I have 5% left over. But we only are really, oops, that was ugly. We're only really concerned. We are only really concerned what happens from here back. This is our critical value. So we just want to know, this is like everything that's going to happen. So if we're 95% sure what's happening, we're really looking at the 97.5%, because this is the 2.5 that we really want. So this is the line that we really want. So to the left of this line is 97.5. And that's the mistake I kept making. Now, if you're using the table, guess what? You don't have to worry about that mistake. You just look at the table. Look at table at 95%. Okay. However, if you're using technology, whether it is StatCrunch or Excel, guess what? Whether it's StatCrunch or Excel, the 95% is really what? 97.5 to the left. This is 97.5 to the left. Same thing. So if we're talking 99%, it's still 99% on the table, but this is going to be like 0.995 to the left and 0.995 on StatCrunch. So here we go. Let's see the critical values, what we're looking for. I'm going to do the critical values for 90%, which I've never really seen, 95%, and 99%. We're going to first do them on Excel, then I'll do them on StatCrunch, and then I'll do them on the table. So let's start with Excel. The first thing we're going to do is Excel. So for Excel, making it nice and big, because somebody told me about that they were too small. So equals normal dot inverse parenthesis. The first one's going to be 0.995, comma. The means for these are always 0. The standard deviation is always 1. That's why we're allowed to use it. So here's our first one, 2.58. It's a different color. So that's how you get this on Excel, 2.58. Now let's get the same idea, right? It's the same, oops, sorry. My bad, right? Well, now I want this at 95%, but 95% is really at 0.975. 1 for the mean, 0 for standard deviation. Sorry, I have it backwards. The mean is always 0. The standard deviation is 1. That's what allows us to do it. So for 95%, it's 1.96. Now let's do one for 90%. So remember on Excel, 90% is really going to be what? 95. Because if my mean is 0, and these are all 1 each, right? But if I want to go 90% of this thing, it's really cut in half. But so from the left of this will be 95. So the critical value for this one's going to be 95. I click cell. I just want to make this a 95%, and that's the 1.64. Now we're going to do the same thing with StatCrunch. We should get the same 3 answers. So let's go into StatCrunch. Let's go into StatCrunch, open StatCrunch. You just need to go to calculator, normal. The mean is 0, the standard deviation is 1. The first one we're going to do is what? 0.995. I got 2.58. Let's make sure that's a match. 2.58. That looks beautiful. Let's change this to 95%, which is really 0.975. And I have 1.6. It's a match. Then for 90%, I need what? 0.95, 1.64. Awesome. Now, finally, we can use what for this? We can use the table. So I can go to eText. It's not being my friend. I guess I got to make it bigger. So you go to eText, right? And we can look at the table and you'll see that they're all a match. Again, sorry for the mistake. We all make them, right? Tables. We want our standard normal to the left. But these are negative. We want this, but we want the positive values. So here are the positive values. The first one we want is what? We want this to be, our first one we want is 99%. Table's not being my friend. Guess what? That's okay. I'm gonna change the table on me. And let's get rid of that. So I got some more space to look at this thing. I want 99%. All right, here's 0.9901, right? And that's 0.99. Oh, sorry. We want 99%. So here we go. I want all the 99%. All right. Use these common values for extrapolation. So the first one is 1.65. And again, this is from the left. So we have to do the same thing. Even in the table, we still have to do the same thing. We still have to use the level divided by 2. It says it right here. So the first one for the 95%, that's like your 90%. I say the 1.64 is 95%. Then they're saying that the 0.995 is going to be the 99%. And where's our 2.58? 2.58. Yeah, there it is. There's the 2.58, which is 90. 2.58. 2.58 is right. Well, they just have them on the bottom. Isn't that nice? So you can look at the table. The table's confusing me for a second because my eyes are hurt. The 90, as you can see, is the 1.645. The 0.95 is the 1.96. And yeah, you can just use it. I was right. So these are the common ones, 2.58. There's your 0.995 right there. So I would just use the bottom of this table instead. Okay. Or use the technology. Either way, it's going to work for you. All right. So let's jump into this new stuff. There's not a lot of problems. There's gonna be barely these on your exam I was looking at. So let's jump into what's important for today. Hopefully that cleared some stuff up. If it didn't, just email me. Sometimes when I'm looking at the screen, it gets a little weird. So here we go. We're doing 7.3. This is the last of the sevens. This section presents methods for using a sample standard deviation to estimate the value of the population standard deviation. So last time we used the sample mean to get the population mean. Now we're going to use the sample standard deviation to get the population standard deviation. We've got the point estimate as last time. So for our point estimate for this one, it says we're using variance. So our point estimate for these is going to be our sample variance. We're going to use that to get the what? The population variance. That's the goal. One conduct a confidence interval estimate of the population standard deviation. We construct the confidence interval using a chi-squared. Sweet. Chi-squared. This is all leading up to when we can finally do a t-test and a chi-squared test, which will finally be nice. Oh, sorry. There's chi. Is the interval estimate of the population. So this is the interval estimate of the population standard deviation. And that is what our CI is now. So our confidence interval is talking about what? The chi-squared is the estimate of the population standard deviation. All right. So here, this is what a chi-squared is. You know, crazy simple. So the chi-squared distribution, a normal distribution with a variance of this. Randomly select independent sample sizes of n for each sample, compute the sample variance. The sample statistics now, here it is. So chi-squared equals n minus 1, which we know is like the degrees of freedom. And then we have our sample standard deviation divided by what? The population one. So this is our test statistic now. The chi-square we can think about as our test, and our goal is to get this guy, the population standard deviation. Okay, that's pretty much what's happening here. Critical values, we denote this by R's for right for right-tailed, L is for left-tailed, and we got a table with this. That's cool. So there's our right tail. We got our left tail. And again, we're going to use our degrees of freedom, which is just the sample size minus 1. So let's look at the table. Yay, there's our chi-square distribution. Tables. This is to the right. So this is for when we got the right tail. We should have one for the left. We don't have a left? Nope, okay, that's all we got. And there was the one we did last time, the critical T's. Here's our chi-squared ones. Notice we've got degrees of freedom, and then we have our confidence interval. All right. Chi-squared, degrees of freedom for 10 and for 20. Notice that it gets more normal with the more degrees of freedom given. Caution. Because the chi-squared is not symmetric, the confidence interval does not fit the form s squared minus e, s squared plus e. We must do separate calculations for the upper and lower limits. Consequently, a confidence interval should be expressed in a format such as, but it cannot be plus or minus e. Okay, so we know chi-squared looks like this, unlike all the other ones we did, so no longer can we do s squared minus e, s squared plus e. No more. No more. So we have to do this in a different light. In a table, each critical value of the table corresponds to an area given in the top row of the table, and its cumulative area to the right of the critical value. Okay. So with a standard normal, we used to do stuff to the left, but because of the shift in this, we're going to be doing areas from the right. All right, so we finally get our first example. So a simple random sample of 22 pulse rates is obtained. Construction of the confidence interval is standard deviation to the right of the critical values, 95% with an n of 22. Find to the left, separating area of 0.25 of the left tail, and find to the right, 0.25 of the right tail. So we have our n, right? We've got a bunch of the stuff that we have. I have my n as 22. You already know what n is 22, so our degrees of freedom is 21. They're also telling us that we have 95%. So we're talking 0.025 to the left and 0.025 to the right. Remember that 5% has to be what? Cut in half. That's why this gets some and this gets some. So right away, we need to find the what? The standard deviation. Oh, they just want the critical value first. So to get the critical value, you can just look at the table. They give us the table. No. All right, so let's actually look at the table because you're not going to get that. Here's our table, right? Remember, we want 0.25. Area to the right has to be 0.025. And our degree, so 0.025 is right here. It's the last one on my little line. We just have to go down to what? 21. 0.025, 21. I believe it's going to be 35.49. Let's see what it is. Let's see what it actually is, you know? There's the 35.479. Cool. We have it to the right. Oh, I didn't do it to the left. All right, let's get it to the left. The critical value is obtained from table in a straightforward manner by looking at it. The leftmost critical value of this also corresponds to, but we must locate that. Oh, cool. I got it. So the first half we get right from the table. The second we have to do 1 minus 0.025 for the other side. So that's going to be 0.975 on the same table. Because if I'm here, if this is 0.25, the other way is going to be 0.975 in opposite. Which makes total sense. So here's 0.975, and we just have to go what? Down to 21. And there's the 10.28. This is on the left. This is to the right. How do they want us to write it? $35.479. Cool. All right. So we got our critical values. I mean, our confidence interval based on that. With the sample size of 22, ta-da, we got it, we got it, we got it. All right. All right, so here are the parts. Now this is the population standard deviation. This is the sample standard deviation. Now n is still the number of terms. We've got our chi-squared to the left. That's our critical value. We got our population variance. This is our sample variance. Here's our margin of error. Then we have our chi-squared to the right. So this is going to be our other critical value. So there's a critical value right, our critical value left. All right, so we need a simple random sample, and it must be normally distributed, even if the sample is large. Okay, so this is stricter, so it has to be normal. All right, we've got our formulas for variance and for standard deviation. Okay, so here we go. N minus 1 x squared over chi-squared to the right. N minus 1 times s squared, chi-squared to the left. And all we have to do, make it standard deviation. Round to one more decimal place in the original data. The summary statistics to the same. Okay. As long as it's random and normally distributed, get the critical values. Once we have the critical values, get the confidence interval. Sweet, we finally have a question. And I bet we're going to do this by hand, but I'm sure we can also use technology. Let's do it by hand first. So we want a 95% confidence interval for this one. We need to know how many degrees of freedom. So ready? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So if my n for this one is 22, this means my degrees of freedom is 21. So let's get our 2 chi-squareds. It was a 95%? I don't remember. 95%. Cool. So for 95%, we know one's going to be 90.975. This is going to be the right-hand side, and the left-hand side is going to be 0.025. Right away, we have that. So first one's the 0.025. That's what's left over to the right. We have what? We have 21. 0.025 and 21 is 35.479. And the other side is going to be 0.7521 is the 10.283. All right, so these are the two things we've got. Area to the right of the critical value. If it's 95%, right? If that's our critical value, we could just think about it like this, right? We want to the right of the critical value. This is going to be the 35. I wrote it backwards. The left of the critical value is this. Guess what? We all make mistakes. That's why we use the picture. All right, cool. So let's keep going. We have our two critical values, is what we need. And now all I need to do is use the formula. Nope, I don't want to, oh, it has to be normally distributed too. So I forgot to check for normality first, like a fool. So let's put it in 76, 80, 76, 54, 86, 74, 74, 74, 66, 84, 62, 60, 78, 50. Now it doesn't matter how big it is. It actually has to be normally distributed for us to work with it. So I got 22. Let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Perfect. The first thing I want to do is I'm going to graph this as a histogram. The smallest one is 52. So I'm going to start with 50. What should I make them each? I'll make them 5 each. So this should give me a good spread of what this looks like. Oops. It's pretty close. Not perfect, but it's pretty close to normally distributed. We can try the QQ. Yeah, I'm taking it. I'm going to say that this is pretty close to normally distributed. That's the first step. All right, now we have our data. And we have our formula, right? But I need like my standard deviation. I need all this stuff, right? So did I lose the stat crunch I just made? Or I just typed them all in? There it is. All right, so we need a bunch of stuff for this, right? See, we need the n, the standard deviation. Oh, sorry, that's the variance. So I might as well go to data, need stats, summary stats, columns, the first one. And all I really need is the n, click and control. I need the variance, not the standard deviation. That's really it. So I'm just going to compute this. So I now have a variance of 106.49, which is what this is. If you want to, if you don't like this, if you hate stat crunch, you know, some people hate it. You know, we can highlight this. Insert undo. There we go. Cool. Now I got them all. I'm just do Control C. So I'm basically just cutting it. I'm just going to drop it into Excel on a new sheet. All right. So if you don't like to do it that way, you just do equals stdv.s. And we got this business right here. So that's our standard deviation. To make it our variance, all we have to do is what? Square it. So either way, we got this 106.495. So to get these two values, right? To get these two error values, all I have to do is take it and divide it by the numbers we have. So you want to use Desmos, you can. It's whatever calculator you can use Excel as the calculator. Doesn't really matter. So I know that this is going to be the square root of 21 times 1.06, one more decimal, so 1.106.5. And we're going to divide this by what? We need the lower one. Oh, no, I did have it right. Did have it right. Sometimes, it's just the way the worm turns, right? 10.283. So there's the first one. So our answer for this example, I believe it's going to be 14.75 is less than the standard deviation, which is less than the only difference I have to do here. Oh, wait, yeah. Wait. This should be the variance, not the standard deviation. Was that the variance? Yes. I just need to double check. That's what S squared is. It's the variance. So now all I have to do is on the bottom put what? 35.479. Oh no, I did have it right. Oh, that's so frustrating. So this was the left, and this was the right. You can tell because it's got to be bigger. So I have 7.9. Should be one more. So it's just 7.9 is less than standard population standard deviation, which is less than 10.3. That's the answer we should get. Let's check it out. I could always be wrong. That's what I think it is. That's what I got. 7.6. Oh no. The 14.2. Ah. All right, so I'm off. Let's see what the errors were. 35.479, 10.283, that's correct. But they're telling me that the variance, oh, they did a standard deviation squared. So they have 9.91. That shouldn't make a difference. When did I use? Did I miss one? I must have messed up my data. Ugh. Ugh. To the 823. Is that A2 to A23? Okay, so I typed it in wrong. Isn't that frustrating? You do all the work right, you type it in wrong. So let's get this correct. And then we'll see how to do it without making a mistake. All right, let's go. Ah, get out of here. Ah. All right, so 76, 80, 76, 54, 86, 74, 74, 74, 66, 84, 62, 60, 78, 52, 68, 84, 62, 66, 62, 56, 74. The last one should have been a 66. And that changed this to 9.91, and it made my variance 98.39. There's the value, 98.3 or 98.4. So we go right back to the Desmos. And it should be 98.4. So brush you out. So we know it's going to be 7.63 or 7.6. And then this has to be 10.283 because this is right. It's going to be 14.2. One little mistake. All right. Let's see how we can do this with computer so we don't make a little mistake like I did. And well, let's make sure those are the right numbers too. 7.6, 14.2. Yes. Okay. All right, let's see if we can do this with I guess StatCrunch. Let's try with the StatCrunch. I should have all the data copied already. Said I should have all the data ready to go. All right, and let's do the T-stat. That's not what we want. We want a chi-square. Do they got chi-square? Let's go. Variance stats. Maybe it's a variance stat. One sample of data. Let's check it out. Talking 95%. Show critical value. Let's see what happens. %. The left critical value says 10.28. 10.28. I like that. The right critical value says 35.47. I like that. That was beautiful. I got my sample variance as that 98. Okay. The lower limit says 58 though. The upper limit says 200. So it at least gives me these left and upper chi-squares here. But what else we got? Confidence interval. Try the confidence interval. Anything else we can do? Oh, here it is. Chi-square. I like it. Let's check this out. So we want a 95% confidence interval. And our degrees of freedom is 21. Sorry, 0.975. There's the 35. Oh, well, we can do it right there instead of the table. There's 0.35. There's the 35, but it only goes to the left. Cool. There's my 95%. Let's see if I try to do it this way. I'm so curious. Nice. I love it. All right. So if we need these two, the between, the lower and the upper bounds, you just put the 95 here and it's going to spit out your answers. However, we do have to do a little bit of math to get this. But at least we can get the critical values this way. Fraction out for the confidence interval. That makes sense. We're just messing with the formula and mess with it as much as they want. All right, here we go. Let's get the sample size. The process for finding the right sample size estimate for your variance for your population standard deviation are much more complex than the procedures given earlier. Okay, for normally distributed populations, 7-2 or the formula. Okay, so it's 95% that the standard deviation is 1%. Okay, we need that many people, that many people, that many. Be 99% the value of the sample should be at least. So for, wow, okay, very interesting table. That this also provides sample sizes when you click it. All right. This table looks scary. Let's just try the example. So we're looking for the sample size. I'm going to try to use the table. All right. We want to estimate the standard deviation. We want to be 99% confident that our estimate is within 5% of the true value. So if I want to be 99% confident that it's in 5% with the true value, I believe we need at least 1,336 people. Just looking at it. That's it. All right, so we're just going to use the table. So for StatCrunch, sweet, there is a way. Or there's a will, there's a way. So summary stats, select within summary. Right. Let's see if I can make this happen. All right, so click stat. Go to variance stats. That's where I was. One sample. I'm just gonna do with summary. But I have the data. Okay. Select confidence interval for it. That's what we have. Enter the desired confidence level. We just have to click compute. But why was it off? Why is the lower limit 25 and the upper limit 200? Wait a minute. Wait a minute. What is the square root? (58.24). What is the square root? That's how it is. Ah, because this is for variance with one standard deviation. So as long as we square root the values, what's it between 7 and 14? Oh, that is so nice. 7.6 and 14.2. Perfect. So all we have to do is square root the lower and the upper limit. That's so easy. All right, cool. Glad I looked at it. Let's knock them out. I think we're ready. All right, so we have 5, 6, 9, 10, 15, 17. 5, 6, 9, and 10. These are going to be so nice and easy. I'm going to just use the stack crunch. It does everything. Form is a little wonky. And we're good to go. That's nice. All right, so number 5. Find the critical value and the confidence intervals in the left and the right. Okay, so number 5 is 95% confidence. Our N is 25, and our standard deviation is 0.24. Let's make it happen. So now I want to do the stats, variance stats, one sample with summary. Our sample variance. Okay. This is the standard deviation. So the first thing I have to do is square this to make it the variance. I have to take 0.24 and square it. That's the first step. That is my first step here. Just using this calculator. So RS squared is what? 0.0576. That's our first step. Oh, wait. I messed up already. This is, no, yeah, we need the variance. Whew, my brain, right? Sometimes the letters mess with me. So I believe it's 0.0576. Our sample size is 25. Use a confidence level, which is what? 95%. I want to show the critical value. I'm going to click compute. The value must be a number greater than 0 and less than 1. I forgot a dot. It's 95%. My bad. Cool. So here we go. We know that the critical value for the left is 12.4. The critical value for the right, which is basically our chi-square, right? These are our chi-squared values. Critical value for the right is going to be 39.36. S is the standard deviation. S squared is the variance. Okay, so I did everything right. This is our variance, so we actually have to square root these two to get the final answer. That's exactly what I'm going to do. So we need the square root of 0.035, the square root of 0.111. So these are the two values I got. And we can check them. And if I messed it up, I will find the error, but I think we did everything right. Point 187. 0.333. All right, this was number 5. So degrees of freedom was 24. Sorry. They say the left is 12.401. Yes, 12.4. They say the right is 39.36. Yes. And our values are 0.19 to 0.33. Sweet, we got the whole thing right. 0.99. 0.33. Beautiful, beautiful. All right, let's go to number 9. Isn't it nice when everything is correct? So number 9. Assume that each sample is a simple random sample from a population with a normal temperature. Okay, so all right, so data set by body temperatures includes a sample of 106. So our N is 106, which makes our degrees of freedom 105. So our sample mean is 98.20. Our sample standard deviation is what? 0.62. So our sample variance, we have to square 0.62. Point 3844. Right? We want a 95% confidence interval. All right, we could do all the math, but guess what? We have everything. We might as well just drop it into Stack Crunch. Let's crunch it up. So I'm just going to go to options and edit this. Oh, sorry. So I'm going to go to stat. Variance stats, one sample was some. Our sample variance, we just found it was 0.3844. Our sample size is 106. We're going to perform a confidence interval of 0.95. We want the critical value. We're going to click compute. We've got our chi-squared to the left is 78.53. I'll go 3 decimals. Chi-squared to the right is 135.247. Then all I need to change these variances into what? Standard deviations. To do that, all I have to do is square them. And that's exactly what I'm going to do. Square root them. So I need the square root of 0.29, right? Is that the right one? Yep, it is the right one. I just like to double check. So I need the square root of 0.2984. I need the square root of 0.5139. Here are our answers. We're already done. We are 95% sure that the standard deviation is between 0.546, because we should kind of match. Oh, there's only 2 in this, so 0.55. And the big one is going to be 0.72. Boom. And that was number 9. Oh, I can check 9. 0.55 and 0.72. This number 9. They rounded it to 0.56 and 0.74. Oh no, 0.55 and 0.72. Oh, and then you're supposed to go on the table to look at it. All right, so I guess I didn't do the last step. What's the last step of this crazy thing? Oh, because we have to turn it into degrees Fahrenheit. I'll let you guys try that yourself. You can change it to degrees Fahrenheit, but that's the start of 5. And did I do 6? Did I skip 6? Yeah, I did. All right, I gotta do 10 at least. Is this the same thing? The same Atkins business? Sorry, I skipped 6. That means I'll do 10 and whatever one's after 10. and 15. I'll do 10 and 15. So here's 10. We got a sample of n, which means their degrees of freedom is 39. The mean is 2.1. Standard deviation is 4.8, which means this like almost the exact one I did earlier, which means the variance is 4.8 squared. $23.04. And we have to be how confident about this one? 90% go. We want our confidence interval should be 90%. Let's make it happen. So our mean is 2.1. Our sample size is 40. Confidence interval has dropped to 90%. Sweet. So our chi-squared to the left is 25.70. Our chi-squared to the right is going to be 54.57. And we have our lower and upper limit, which we just have to do what to them? We have to do the square root to them. That's it. All I need to do is the square root of 1.5 and 3.187. I'll let you guys do the thinking part of it. And this is going to be 3.187. All right. I think this is the tiniest standard deviation ever, but I think that's good. There's barely any variation in it. So I think this is good to know. I know the mean sucks, right? Because you're barely losing any weight, but at least we can be really sure that the amount of pounds that we're losing, like this is such a small variation. The amounts of pounds we're losing, at least we'll be sure we're going to lose between 1 and 4 pounds. Okay? At least we could be positive that, sorry, the mean was 2. I think it was between 1 pound and 4 pounds, but there's almost no variation. So we're definitely at least going to drop that much. All right, here's 15. This will be the last one I do for this. We made it to 15. Listed below are this, what do we have to do? Sorry. Oh, they already tell us it's a normal distribution. I was about to check it. You know what I'm gonna do? I'm gonna check it. I don't trust anybody. Listed below the student evaluation scores of professors. Oof, I hope you guys think I'm doing a good job. If it's shitty, just let me know. In Appendix B, construct a 95% confidence interval for each of the 2 data sets. Does there to be different variations? We have to do the same thing twice. This data set and this data set. So we got to do this for men and women. Sorry. Whoa, what just happened? Sorry, I don't know what's going on. We're all the way down at 7.3. We basically have to do this twice. They're telling us that this is it, right? They're telling us that. What would I do? I would actually go to each data set, do a histogram and a QQ for both, just to make sure, right? Like, I don't know. It's hard for me to trust that, but I will for this case. So we have to do this twice and just look at the variation of both. That's what we're doing. We could do the whole thing by hand. Because we have the data, it's really easy just to put it in. Obviously, I did erase, you could like rewatch it, but you might as well just, you know, do it. I'll show you that you can do a few of these at once. So here we go. I call this one females, call this one males. So 4.4, 3.4, 4.8, 2.9, 4.4, 4.9, 3.5, 3.7, 3.4, 4.8. So there should be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. All right, now let's get the guys. And 6, 4.1, 4.1, 3.5, 4.6, 4.0, 4.3, 4.5, and finally 4.3. All right. So we have to go to stats, variance stats. We have two samples, but we don't really want to compare them. So we're just going to go with data. And I'm just going to do two of them at once instead of trying to do a comparison of both. So we're just going to do two of these at once. Show the critical value. I want this at sorry. Show critical value. We can do dot plots and markers and a QQ plot. Let me just do it again. So I'm in stats, I'm on variance. I want to do one sample with data. Go in here, show critical value. Sorry, it was just really loud. It yelled at me. I got scared. Keep this done. All right, cool. We got our variances. We got our left chi-squares. We got our upper chi-squares. We have a left limit and upper limit. Interesting. Okay, it's pretty normally distributed for the females. Definitely for the males. Got an outlier here, but that's okay. So all this looks nice. Is there a difference in variation? Yeah, look at that variation. Guys are about 12%, girls are about 51%. That's kind of wild. The left and the upper are barely anything though. Oh, that's just because it's the degrees of freedom and the percentages. So these two should be the same. Yeah, they are the same. But notice this 0.24, 1.73. Yeah. So this means the girls varied a lot in their variation of the professor, the guys didn't. So let's look at it. That was right. The confidence interval. What? Am I looking at the wrong place? I was. Okay, good. Oh, they're telling us that they overlap, so that there's not a difference. All right, so let's actually write them out and see. They're saying that there's no real difference. So let's look at this. Let's make it the confidence interval. So that's our lower limit and our upper limit. That's of the variance. So what do we have to do with them? We have to discriminate these. So the girls is 0.25, 0.245, 0.246 rounded. So this is the women. The women are between 0.50, and then the other side is 1.732. 1.32. Okay. That's the girls. Let's put the boys. So the boys are between 0.05888. The boys are between 0.24. The reason why I thought it was so different is because I was looking at the variation, which it isn't standardized. So the variation always looks so different, but once we do the square root, then it becomes looking like the normal number. See, like I thought this was such a big jump, but that's because it's variance and it's not standardized to the actual numbers they gave. That is why I was wrong when I looked at the values. All right, let's go down 0.4148. 0.64464. So between 0.24, 0.6, 0.5. So there is a little bit of overlap here. And they're saying it's very small. That would cool. Now, if we look at these numbers, the variance, I don't think that's negligible difference, but that's just me. I guess it does overlap on this one. So, we all make mistakes, right? I hope this one was useful. Try number 6 and whatever one I left out. I hope this one was clear for you. And I'm going to make one more today on the last part of chapter 7, but we're pretty much towards the end of this. So take care.